All right, let's take a look at some 2D dynamics. 2D dynamics. So these are problems involving forces that are acting at angles. So instead of the previous problems that have forces acting in just the x, just the y direction, we're now going to have forces acting at some in some quadrants. Now the big change between 1D dynamics and 2D dynamics is now in 2 dimensions. We need to make sure we organize our forces into the x direction and the y direction. So let's take a look at how this looks and how we can use this to solve problems with unknowns. We have a block of mass m, 15 kilograms, is suspended at rest by 2 strings attached to walls, as shown in the figure. The left string is horizontal and the right string makes an angle of 50 degrees with the horizontal. What is the tension in the left string? So we have 15 kilograms here, and we have 50 degrees right here. And we want to know what this force of tension is. So the strategy for problems like this one with strings and objects that are hanging is identify what you are drawing your free body diagram of. The free body diagram of just the mass might be an appealing choice, but the free body diagram of the mass is just going to be force of gravity and force of tension, this string right here. Those are going to be balanced forces, but that doesn't really help us figure out anything about the force of tension on that left string. So let's go ahead, instead of drawing the free body diagram for the mass, let's go ahead and draw the free body diagram for this ring right here in the middle. Let's do that. And since we have 3 different forces of tension, let's go ahead and can call this one force of tension 1, force of tension 2, and force of tension 3. Force of tension 3 is what we want, by the way. And let's go ahead and let's draw out our 50 degrees right there. And let's also make one last change. Now, since the mass hanging has the force of tension upward and the force of gravity downward, and those are balanced because the object is not accelerating up, nor is it accelerating down, I'm actually going to replace this force of tension 1 with mg. That is the mass of the block times the acceleration due to gravity. That's going to help us out. So where do we go from here? Let's go ahead and utilize our new skill. Let's figure out what forces are acting in the x direction and what forces are acting in the y direction. And let's also come to an agreement that since there is no movement whatsoever in this diagram, that both accelerations, the x and the y, are going to be 0. So let's go ahead and replace this with 0. That isn't always going to be the case. We're going to do another example problem in a moment where that is not true. But for now, we know that the F net in the x direction is equal to 0, and the F net in the y direction is equal to 0. Okay, now let's break these up into what they truly are. We are going to, I see one force in the x direction that is very clearly just in the x direction. That is the force of tension 3, our unknown force. And I see a force that's in the y direction, mg. That is the mass of the block times the acceleration due to gravity. However, this force of tension 2 up here is a little bit tricky because it's neither in the x nor in the y. So what we're going to do, just like in our projectiles unit, is we're going to split this up into its components. We're going to say we have a force tension 2x and a force of tension 2y. Now, I'm going to redraw those forces and make a right triangle. Here's force of tension 2. Here is force of tension 2x and force of tension 2y. And there's our 50 degrees. Let me real quick, since we're going to be doing some Since we're going to be doing some math here with trig, let me make sure that I am in degrees, which I am. And let's get these two components. Force of tension in the x, force of tension 2 in the x is going to be ft2 cosine of 50 degrees. ft2y is going to be ft2 sine of 50 degrees. All right, awesome. Let's go ahead and lasso these over. We're going to bring these over, and we're going to be continuing down the algebra there. So now let's just do all the right forces minus the left forces. Everything's in equilibrium right now, and so we're just going to be adding and subtracting magnitudes, and it doesn't really matter which way you choose to be, your positive or your negative. So I'm going to choose right to be positive and up to be positive. That seems pretty uninspiring. So we'll replace F net in the x direction with all the forces in the x direction. We have ft2x minus ft3, and that's going to be equal to 0. In the y direction, let's go ahead and do the up forces. That is ft2y minus the down forces, mass of the block times acceleration due to gravity. Let's go ahead and divvy these up once more. Let's go ahead and replace our ft2x with ft2 cosine of 50 degrees and ft2y with ft2 sine of 50 degrees. And let's just acknowledge what we have here. We are looking for ft3. We also do not know what ft2 is. We do have mg, however. So I hope you can see what I'm seeing. We're going to use this side in order to figure out force of tension 2, and then we're going to plug it into this side to solve for force of tension 3. Let's do that now. I'm going to go ahead and add mg onto both sides, and I get force of tension 2 is equal to mg times the sine of 50 degrees. Let's go ahead and plug that in. We have a 15 kilogram block multiplied by the acceleration due to gravity, and if you're doing this yourself, you definitely show all your units. We're going to then take the sine of 50 degrees. We are in degrees, we checked, and we get a force of tension 2 is equal to 191.9 newtons. Awesome. Cool, so let's go ahead and let's use that. And let's plug that into the other side. ft2 cosine of 50 degrees minus ft3. We can rearrange this just a little bit to get ft3 equals ft2 cosine of 50 degrees. And this is going to allow us to solve really quickly. 191.9 newtons multiplied by the cosine of 50 degrees. And that's going to be equal to 123.3 newtons. And that's going to be our answer. Let's take a moment, let's acknowledge something. What we said was that the difference between the x component of the second tension and the third tension was equal to 0. That was essentially saying that this component and this force vector added up to be 0. We also said in the y direction that the force of tension 2 in the y direction, that component, and the force of gravity also balanced out. So this force and that force were equal. In the end, what we have is three vectors that all cancel each other out. We have the force of gravity mg, we have the force of tension 2, and then we have the force of tension 3. Now what I've drawn here is a sum of three vectors whose vector sum is equal to 0. So that's why they kind of ended up making the full train of tip to tail to tail to tail. Sorry, tip to tail, tip to tail, tip to tail. So this is a good conceptual idea, but not a triangle that you should be drawing right away. We should be splitting our vectors into components and dealing with the net force in the x direction and dealing with the net force in the y direction. Now this was an easy problem because both our accelerations in the x and the y were 0. Let's take a look at our very first problem on the homework assignment and figure out what would happen if our acceleration is not 0. So you are successfully pulling a mass at a non-zero acceleration at some angle from the horizontal across rough dirt as shown. Okay. Solve for the acceleration of the mass if the magnitude of the force is 200 newtons, the mass of the block is 30 kilograms, the kinetic friction coefficient is 0.45, and the angle theta is equal to 10. So, unlike the previous problem, let's go ahead and let's draw the free body diagram for the mass. We have the mass, we have that force of the pull, that force vector F. We have the force of gravity downward. We have some kinetic friction, which is going to be acting against the force of the pull. And the normal force. Now, I'm only going to draw the normal force about that large. I want you to take a moment and see if you can figure out why I only drew the force normal that big. So typically, when we have objects that are being pulled horizontally, such as this, the normal force and the force of gravity need to balance each other out. However, the force we are applying is not totally horizontal. Instead, now it's being pulled up at an angle, which means there is some component of this force vector which is kind of being added on to the normal force. Whoop, I didn't draw that big enough. Added on to the normal force to cancel out the force of gravity. And so right away, hopefully you can see that there's going to be some interesting stuff going on in the y direction, and that's going to definitely connect to the x direction. Let's take a look. F net in the x direction is equal to ma in the x direction, and F net in the y direction is equal to ma in the y direction. Let's go ahead and let's just plug in what we know for both of these and see where it takes us. Because our goal is to figure out the acceleration, that guy right there. Ooh, that's a bad color. That guy right there. So, let's split up our components. We have F at an angle of 10 degrees, so Fx is going to be just the force times the cosine of 10 degrees. And Fy is going to be F times the sine of 10 degrees. And as per usual, let's go ahead and lasso this stuff over. Whoa, I'm taking the problem with me. That's okay. That's okay. It's a picture. So, F net in the x direction, there are two forces in the x direction. We have Fx minus F of friction kinetic equals mass times acceleration x. Let's go ahead, let's break this down a little bit more. What I'm going to do is I'm going to replace this with F cosine of 10 degrees minus the coefficient of kinetic friction times the normal force. And I think that is about as far as we can go. We don't know this, and we don't know this. Let's try the y direction. We have the normal force plus the y component of our force vector, which is going to be Fy. Those are the two upward forces, so I'm going to add them up. And then to that, I'm going to subtract the force of gravity. And this object isn't accelerating upward, nor is it accelerating downward. And so we can say this is all equal to 0. So we get a really nice equivalence here that our normal force is going to be equal to the force of gravity minus the force in the y direction. I'm going to actually replace that force in the y direction, hope you guys don't mind, with F sine of 10 degrees. Awesome. What don't we know in this equation? We don't know the normal force. Actually, so what we could do, if we wanted to, we could totally take this and plug it right in for our normal force up here. However, let's hold off. Let's go ahead and let's solve for a value. Sometimes there's something to be gotten from a problem by plugging in no variables and just seeing all the symbols work together. However, this time around, since this is one of the first times we've done a two-dimensional dynamics problem, let's go ahead and plug in some numbers. The normal force is equal to the force of gravity, which is mg, minus the force times the sine of 10 degrees. And let's plug in some values. We have the mass of 30 kilograms times 9.8 meters per second squared. And then we have 200 newtons, if I'm not mistaken. Yeah, 200 newtons multiplied by the sine of 10 degrees. And we have kilograms and meters per second squared, which are going to multiply to be newtons. And then we have newtons times the sine of an angle, which is unitless, so it's going to be just newtons. So yeah, we could totally subtract these two. We'll do 30 times 9.8. And to that, we're going to minus 200 times the sine of 10. We get 259.3 newtons. That is our normal force. Our normal force would usually be, and I'm going to try and bring your attention up here to the calculator. The normal force would typically be 294 newtons. However, since we're pulling up on the box ever so slightly, that means that some of that normal force that the ground would have to apply is kind of being helped out by the person pulling upward. So the person is kind of lifting the box ever so slightly off the ground, which is decreasing the normal force just by about 30, 40 newtons. Okay, we have our normal force. Let's go ahead and let's plug it in along with all of our other values up into this problem up here. So hopefully you see the pattern here. We set up our f naught x, we set up our f naught y, and we see if we could figure out a system of equations. Sometimes that's what we're going to have to find, a system of equations that will help us determine an unknown value. So we have f cosine. I'm going to go ahead and bring it up here. F cosine of 10 degrees. Let's go ahead and plug in some values. Whoa, my bad. We have 200 newtons times the cosine of 10 degrees minus the coefficient of kinetic friction, which is 0.45, times our normal force, which we just solved for. It's not mg, it's 259.3. And that's all going to be equal to ma. 30 kilograms times acceleration in the x direction. So let's go ahead and let's solve for the acceleration in the x direction. I'm just going to do this all in one go. We have newtons times a trig function, which is newtons. And then we have our coefficient of friction, which is unitless, multiplied by newtons. So we're going to have newtons minus newtons, and we're going to be dividing by kilograms. And so we know our units are going to work out just fine. 200 times the cosine of 10 minus 0.45 times 259.3. And we're going to divide both sides by then the 30 kilograms. And we get an acceleration of 2.67 meters per second squared. So that's the first problem in the problem set for 2D dynamics. Go ahead, and I recommend trying to not follow along and do it on your own. And just remember our steps. First, we drew a free body diagram, and we identified what vectors we needed to split up into components. Then we wrote our two equations of motion, our two Newton's second law problems, F naught in the x and F naught in the y. And then we just solved. We actually hit a little bit of a dead end right here, which was totally fine. We just then solved for the y, and we found that, hey, the normal force that we got from the y direction, we can use in our x direction. All of these problems are going to be more than one step. It's very rare to have a problem that's only one step. So that means just either A, getting used to the patterns that you find, or B, just building together a bunch of survival skills to approach problems with. That's all. Thanks for watching.